structural effects, this is looking at the structures. The first thing is the leveling effect. And the leveling effect states that the strongest acid or base that can exist is a function of the solvent species. So, for example, for water, if your autoionization, the acid form is H3O plus and the base form is hydroxide. If you use the solvent as ammonia, so if you'll notice ammonia self-reacts, so the acid form is NH4 plus and the base is NH2. Now, you can do this with any thing. I'm going to go ahead and add another page here. So, for example, I'm going to take methanol. That's methanol. It's got a proton. It can donate, and it's got lone pairs on the oxygen, so it can act as a base. So what's going to happen is one form acts as an acid and one form acts as a base. So if that one donates the proton, the other one accepts the proton. So when you look at it, this is the base form. It is the conjugate base. This is the acid form. So this is the conjugate acid. You can do this with any molecule given that you're told acts as a solvent, and so it will level. Now, the reason why this is actually critical is most reactions you do in this class will have water as the solvent. That is not true when you get to organic, especially. And so the problem is what's a strong acid in water may not be a strong acid in like ammonia or whatever. So that's why we have to look at the leveling effect. So let's look at structural effects, family trends. As you go down a family, the acidity tends to increase. With bond polarity, as the polarity increases, the acidity also increases. And some of these actually compete, and it's a function of what their environment is, but if you're looking at a trend, you can go either way. Bond dissociation, as the bond strength tends to decrease, the acidity increases. If you think about it, it's easier to break the bond, so it's a stronger acid. The atomic size, as it increases, the bond length tends to increase. The acidity tends to increase. This has to do not only with bond length, but it has to do with polarizability. Remember, we discussed that when we talked about electronegativity. Electronegativity back in the Lewis structures. All right, as you increase a negative charge, you're going to increase your attraction to H+. Your acidity is going to drop. Your basicity will increase, but your acidity is going to drop. Okay? So again, these are just trends. And sometimes you have competing process and it works accordingly. So if you look at it, according to this, the strongest acid is down here with HBr. It gets weaker as you go up and over because you're going down the family, etc. Okay, now the other rule is oxyacids. As you increase the number of oxygens, you increase the acidity. So H2SO4 is a strong acid, but H2SO3 is not. Perbromic is strong. Chloric is strong. Chlorus and perchlorus are weaker. So we've done this here. I've listed bromine. These are all chlorine. So as you increase the number of oxygens, you increase the acidity. Okay, if you have the same number of oxygens, you look at the electronegativity of the central atom. As the electronegativity increases, the acidity increases. So if you're looking at HBr and HCl4 and HBrO4, then they're exactly the same number of oxygens, but chlorine is more electronegative, so this acid is actually stronger. Sulfur is much more electronegative than is selenium, so this is a much stronger acid. The other special type, and it's a huge class. If oxyacids are the ones that are carboxylic acids, they form the largest class of organic acids. When you get to organic, you're going to be inundated with them. They contain a carbonyl group, and a carbonyl group is the carbon double bond oxygen, and an alcohol, which is the OH group. So here's your alcohol, here's your carboxylic acid. Together, this forms the carboxylic acid. So if you'll notice, these all have carboxylic acids in them, okay? The reason that carboxylic acids are strong is they have extra stability in resonance structures. If you'll remember back to resonance structures where you're moving the electrons, well, what happens is that this pair moves here, this pair moves here, so you end up moving the double bond around. It's kind of a moving target, so the negative keeps moving around. Because the negative keeps moving around, it's harder to get it to react as a base, which means that it's a stronger acid. Because acidity is a function not only of whether it can donate an acid, but whether it can be what the conjugate structure looks like. So this is why this is actually a huge class. The other reason is in its amphoteric properties associated when it forms amino acids, and you can read over that as you go. And again, in biology, in biochemistry, in organic, you'll encounter this a lot. Now, the other thing is oxides and acidity. Non-metal oxides tend to form acids. This is SO2 plus water forms H2SO3, which is acid rain. Metal oxides tend to form bases. So for example, if you had calcium oxide and put it in water, then you'd end up with calcium hydroxide. And some are amphoteric. This was like aluminum and a number of the other ones. And a lot of the amphoteric ones tend to be around the zigzag line, but I am most concerned with your ability to identify the oxides here. Okay, and here is a figure from McGraw-Hill, which you remember, here's your zigzag line. So these tend to be amphoteric, but mainly go with the acidic and basic set.